Good morning, everyone. I'm TJ, and today I want to show you a nonlinear static simulation in NX SOL106. It's a snapback of a cylindrical shell, which is a tough numerical challenge to the solver. And I will use a benchmark study published by P.G Bergan. First, I will show you some model validation, how you can ensure that the model has the right boundary conditions, loads, and materials. And then I will show why load and displacement control will fail. And I will show you how you can use the arc length control to guide the solver through the numerical problems. The paper where the benchmark is published is called Solution Techniques for Nonlinear Finite Element Problems. And as you can see on the image here, the model is quite simple. It's a cylindrical shell with radius 2,540 millimeters. The length is equal to 2 times L on this figure, which is 508 millimeters. And the angle is 2 theta, which is a total of 0.2 radians. And the E modulus is 3102.75 megapascal. It's actually wrong in this figure. And the Poisson ratio is 0.3. The challenge in this case is that you see the behavior is really highly nonlinear. We see it starts in a linear way, but then the stiffness reduces, and on the top here we have a limit point with actually no stiffness. And then the stiffness becomes negative, and in this area it's actually infinite negative, and then it turns in the turning point and becomes infinite high or positive. And then it snaps back before it absorbs more force again, and we have this behavior after the last limit point. You can tell that there are two singularities here. If we use force control, we have zero stiffness here, and we can have some kind of snap through behavior here, because the force control will not be able to capture this snapback behavior. If we use displacement control, it actually becomes singular in this area where we have this turning point. So the displacement control is neither applicable in this case. We can also tell that if you have a load level at 0.4 kilonewtons, we have actually not only one solution but three solutions. And also if we go at a certain displacement, in central displacement, we see that there is not only one but actually three solutions as well. So this is a highly nonlinear problem, and neither force or load control or displacement control will work. That's why arc length methods have to be used. And as we see, there is an application point here in the middle where the load is applied. Here is the FEM model, and we see that the default thickness of the shell is 6.35 millimeters. The Young's modulus is 3102.75 megapascal. Poisson ratio is 0.3. And I've used an element size of 35 millimeters, and I used sequad 4 elements. The force which causes this snapback behavior is applied in the middle, and it's a total of 600 newtons, and that should represent a total displacement of roughly 30 millimeters or 300 millimeters. We have two edges which are clamped. The X, Y, and Z translation is restricted or constrained, while the rotations are free, these two edges. Before you do a nonlinear analysis like this, that probably will cause some problems. You should do a linear analysis, and then you can use SOL101 or SOL106 as well, but then you have to turn off the LG disp option. As you can see here, the system has a quite linear stiffness initially, at least up to a force level of 200 newtons. Then you see the nonlinear behavior kicks in. So if you apply something like 500 newtons, you see that the linear analysis will give you an estimate of the total displacement. It looks like it's like 6-7 millimeters. But that will cause some residual forces because the system is really nonlinear. And you see here the correct solution is roughly 9 millimeters, I guess. But if you run on linear analysis, you will at least have an estimate of the total of the displacement. So then you can verify that the model is working fine. What you have to do is to create a simulation and select SOL106. And you have to make sure that the bulk data option here, large displacements, LG disp, is switched on. Otherwise, you won't be able to capture the nonlinear behavior, and you will only run a linear analysis. And the solution properties to be set are output requests, nonlinear parameters, and you have to activate arc length method parameters. And these can be created in the solution case control menu, or they can be selected in the case control sub menu or the subcase menu. But you can also define them directly in the case control sub menu, I think. These are the settings you have to switch on. You have to go to case control, and the nonlinear parameters to use are the number of increments. You can use 200 or 300. It will work with 200. The intermediate output flag must be switched to yes, or I use all, because then I can check the results at each time step. And the iterations before update, I've set it to 1 because I want the tangential stiffness to be updated for each iteration. And I use error tolerance for load. That means residual force limit to 1 Newton, which is a quite strict demand because I want to give you a nice plot. And the total load, I guess, is like 60 kilonewtons, if I remember right. Then you should switch on some output requests in order to plot the results that you want from this study. And you have to switch on forces, enable force request. You should also switch on residual vectors when you do analysis like this, because you want to check that the residuals are below a certain limit or within your tolerance. And it's sometimes nice to plot the strain energy as well. Then, in order to run this simulation successfully, you have to switch on the arc length method parameters. And in this case, I used all the default parameters, except for maximum increments was set to 500. But I think the default settings will work. When you want to display the results, you must remember to switch the intermediate output flag to all, which I already mentioned. Then you can animate the results for each time frame or load step. And you should make sure to set the displacement scale to 1 in the post view menu, because otherwise the first displacement for the first iteration will look quite crazy. It will be scaled to 10% of the model size. And finally, you would like to plot some curves in order to get this snapback behavior. And you have to do it in 2 steps. First, you have to create one graph which shows you the displacements versus load step or iteration. I think you should use iteration. And then you have to plot the force versus iteration and save those in 2 different AFU files. Then you can go to the force displacement graph feature called toFunction, which you will find in the resource bar, the function resource bar tab. And then you can combine those two curves or graphs, and you can create a new graph that shows you displacements versus forces. Actually, in this case, you could find the same, almost the same shape using iterations, force versus iterations, I think. But this is the way to create a nonlinear response curve like this. So if you are an NTNU student, you can download these parts from the NX-portalen server. If you're not an NTNU student, you can probably create this model from scratch, or you can mail me and I can provide the models. Here is the CAD model, and as you can see, it's a cylindrical shell, and the dimensions are given in the PowerPoint. My first task is to mesh it, so I go to pre and post, and I create a new FEM and simulation. I accept the default names, and I don't want to create an idealized part file. Here I have to select SOL106 with global constraints. And then while I'm in this menu, I can set up the numerical parameters. I can specify some new output requests, and I want to have a look at applied loads, because I want to apply a load in the center of this cylindrical shell. Also enable force, strain energy. Sometimes that's useful when you do simulations like this. And I think that's it. And then I go to not output requests, nonlinear parameters, and number of increments. I think I don't use 200 as I said during the PowerPoint. I increase it to 500 to make sure that I have enough increments. The intermediate output flag is critical in this simulation. I can't set it to all, because then the solver will fail when it reaches the limit point where the stiffness is 0. So I use yes, and then iterations before update. 5 is probably okay, but I can ask the system to update the tangential stiffness matrix for each iteration, so I can set it to 1. I think I can leave the default parameters for load and work. That's the residual load. And I think I can keep the other factors here. They are fine, I think. Okay. Then I have to apply the arc length method. And I want to set up the maximum increments. I give it the same number here, 500. And else I keep the same default parameters. So then we have already specified the solution setup. But we also need to select those parameters in the subcase later. But now we are going to mesh this model. And let's use shell meshing, 2D mesh. I want to mesh those 4 surfaces. The element size is 35 millimeters. That will work fine. And I want to make a destination collector. And I want to call it thin shell 6.35, because that's the thickness I want to use. And I want to create a new property. And my thickness is 6.35. And I want to specify a material. So I choose material, and I can create a new one. And then I go to the Young Poisson ratio is okay, but Young modulus, I think it was 3102.75. And then the Poisson ratio was 0.3. I don't have to give any mass density, because this is a static analysis. And I want to give it a name. Let's call it snapback material. OK. Then we have the right material, we have the right thickness, and that's OK. Then we have given the property a name, thin shell 6.35. That's OK. And then we are ready to mesh. And there we have the mesh. Then it's one thing that is critical, and because these were individual faces, they might not be connected, so I want to stitch them. And where is that command? I could stitch them, or I could merge coincident nodes, but let's do it the best way. I go to Insert, Model Cleanup, and there is the command Stitch Edge. And then I select all faces. I press Apply, Cancel, and then I'm asked to update the mesh. Then everything should be ready for the solution. While I'm still in the FEM file, I could do a couple of checks on my element model. And one is to make sure that I have the proper thickness, so I can highlight my 2D mesh, edit display, and I can display the element thickness on my model. And this looks good. Switch it off again. And then there is one check that you should always do when you have a shell model, and that's to check for duplicate nodes. If there are any free edges, they might cause duplicate nodes, but here I see that there are no duplication and no free edges. So then I can activate my sim file, and I'm ready to apply boundary conditions and loads. First, I could apply the constraints. I can apply a user-defined constraint on these edges. There are 4 edges. And then I can constrain the translational degrees of freedom. I want to keep my rotational degrees free, so this means that the cylindrical shell is hinged. There we are. And then I go to loads, and I create a new load, force, and I switch to static wireframe view, and I select the center node where I want to apply the load. And the load should be maximum 600 newtons, and that load will be applied in 500 increments. Then I have to specify the vector, and it's positive set, because set is in this case pointing downwards, and I press OK. So there we have the load, and we have the boundary conditions. The next thing I have to make sure is that the setup I defined in solution 1 is selected in the subcase here. So I must make sure that my structural output request, which I define, is selected, my nonlinear parameters are selected, and my arc length methods are selected. Because the setup in the solution 1 can work as a repository for different setups, and they have to be selected in the individual subcases. Then I almost forgot something very important. In the solution setup, there is one switch which has to be turned on, which I forgot. And it's this one. It's in the bulk data menu, and it's large displacements. If this one is off, I will run a simple linear analysis, but when I turn it on, I will run a nonlinear analysis that will be able to capture my nonlinear snapback behavior. So now it's on, and I can then run my simulation. I press Solve, and NX will show a simulation monitor, which gives me information about the performance. And here I can plot graphs, and I can show how the solver is performing. And here we see the residuals with respect to displacement, force, and work, which are the default parameters specified in the simulation setup. And now the simulation is completed, and we are ready to run. But first I could check that there are no error messages. I press on this job, and I press on Analyze Job Information. And there are some warnings, but no fatal errors. Then we can do the post-processing, and I switch on my solid view again, and I double-click on my structural results. And the first thing I want to do is to animate the snapback behavior to see if it's as expected. I then select nodal displacements, magnitude, and as usual, NX is scaling my displacement to 10% of the model size, and when I run a nonlinear analysis, this must be set to 1. Absolute. Okay. And so I want to animate this, and I press animate. And I don't want to animate results, but iterations. And here we see I have 322 iterations, and I don't probably need to display all of them, so I could choose to display each fourth of them, and then I press OK. And then you see why this is called a snapback behavior. You see that the middle is pressing down, and then the edges are following, and suddenly they snaps through, and the middle will pop back again, like just now. And this is a very demanding simulation for a solver, and it's not easy to capture. But with the arc length method, you can do it in NX. Looks good. Then we stop the animation, and I want to check that I can output the same graphs as shown in my PowerPoint. And then I select displacement, set displacement, and I switch on to the create graph command. And I don't want to use load factor as x-axis, but iteration number. And then I will step from iteration 1 to 322. And I select the displacement in the center, across iterations, displacements, OK. And then I plot the curve. And this looks quite interesting. I then have to save this image, capture image. No, sorry, not capture. I have to save graph. And then I call this displacement, disp, I could call it. Let's check disp.afu. And I have to, of course, select this one and add it here. Then I can save it. Then I made a file called disp.afu. Can cancel this one. And then I want to plot the force. In this case, I think it's not the reaction force, but applied force. And I select the force in the set direction, and then I create another graph. I select the mid node, and it's not, I don't want to display it as a function of the load factor, but the iteration number. It wouldn't make any difference really, but that's just a choice I'm making. And then I press OK and create a plot in a new window, and it looks like this. Let's save this one. I save graph, I select the force, and I want to give it a name, force. Okay. Then I've saved those two curves. And the reason why I did that was that I want to plot the forces as a function of displacement. And I then go to the resource bar, XY function navigator, and I go to associated or user AFUs. And here we have the two graphs which I created. and then I can mark them, right click, and I use this function called to function, and I use the first choice here and I plot it. And yeah, I guess this looks good. You can see that we have been able to capture the nonlinear behavior. We reached a limit point, then the stiffness becomes almost infinite negative, and then we reach the turning point and it snaps back, and suddenly the stiffness becomes infinite high. And then we come to the new limit point, and then again the structure is able to capture the load, and we see an increase. If you want to clean up the view of this graph, you can select editing, and you can change the heading, for example, user defined. We can say force deflection curve, apply. Then we could set the range. We could set the force range to from not auto range, but 0 to 650. Apply. And then, oh well, we have to actually use some negative value, minus 200 perhaps. Let's try that. Still too low. We can go to 350. Still too low. 450. There we are. Okay, and then we can set the x-axis range from 0 to 30 millimeters. So there we are. Yeah, that's all I want to show you. I can conclude that NX is capable of solving really highly nonlinear simulations like this by using the arc length method, where both force and displacement control will fail.